Hello and welcome. The purpose of this video is to walk through common pitfalls in the second key assessment in Year 2 IB Chemistry. All right, question 1. Deduce the equilibrium constant expression for the decomposition of PCl5. So one of the first mistakes that I saw here was not recognizing this decomposition of PCl5. We learned last year decomposition reactions. You start with one reactant, you end up with the products. They tell us that from this graph I can see it should separate out into PCl3 and Cl2. Some people thought because they started with Cl2 that it had to be a reactant, but the reaction is decomposition of PCl5. So they did start with some concentration of Cl2, but then we see that that concentration increases once the time starts, so that does mean that it's one of my products. The other thing that increases is a product, and of course my reactant would decrease to reach equilibrium. All right, the other common pitfall I saw was not recognizing this word expression. The expression is just plugging in the concentrations, not solving. Most of us remembered how the expression works, that you have the concentration of your products multiplied by coefficients, which was not a thing in this case. All of the coefficients were 1. To the power of the coefficient, sorry. And then over the concentration of your reactants, of course, multiplying anything together. And so in this case, we should have had the concentration of our products was PCl3, Cl2, over the concentration of my reactant. No powers because all of the coefficients are 1. All right, AI. This one was a little tricky. What was the factor responsible for establishing a new equilibrium? And we see the new equilibrium right here. One of the keys here was recognizing that we were in a sealed flask. So when I think about Le Chatelier's principle, well, if the flask is sealed, that means that I did not increase the concentration or decrease the concentration of anything. It also would not make sense to change pressure because generally we do that by changing volume. The only way to change pressure in a sealed flask would be to bring it to a new altitude, and that didn't happen between this time and this time. That wouldn't happen instantaneously. And so the only change that makes sense is a temperature change. And now I just need to figure out if temperature increased or decreased. So I see that my reactant concentration increased. All right, so that means that I shifted left if the reactant concentration increased. In this case, the forward reaction is endothermic. That means the left-hand reaction is exothermic, or the reverse reaction is exothermic. The way that I favor an exothermic reaction is to decrease temperature. So in order to get points here in B, I needed to see something about the shift and decrease temperature. Not just saying favoring products or reactants, but I did need something about shift to get both points. All right, question B. You had actually had access to this mark scheme from T7 day 5. This was the mark scheme that we saw in the slides and the same mark scheme I used in the question. So some people here, the common pitfall I saw was some people just said Q, non-equilibrium, KC, equilibrium. You actually did need to specify concentration. Notice in the mark scheme, you did need to be really specific about what Q and KC are. If you just say equilibrium and non-equilibrium, you're not proving to me that you understand that Q and KC are about expressing the concentrations of reactants and products we would have at equilibrium. You could have also said something about the time that it was measured. Question C, this was only an HL, not an SL. This was asking you about Vesper theory for PCl3. And just to remind you, you had really recently seen a review of Vesper theory The review that we had seen, of course, was trigonal planar. In this question, PCl3, well, if I draw out my Lewis diagram, phosphorus has 5 valence electrons, 1, 2, 3, 4, 5. It's going to make 3 bonds with Cl to make Cl3. Lone pairs around all the Cl's. This would be tetrahedral. Molecular geometry would be trigonal pyramidal, but this asks for electron geometry. So you had really recently seen a review of Vesper, so fair game for the test. Anything's always fair game, but especially fair game if you'd recently seen something in a homework problem. All right, question 2. Question 2A, this was both a standard level and high level problem. So this problem was asking about theoretical yield. We have, of course, been practicing theoretical yield for a long time. In the first key assessment, there's a theoretical yield problem. The most recent time that we'd practiced going into DM cubed was in that special stoichiometry office hours I'd hosted, where we reminded ourselves of that molar gas constant. So many of us did theoretical yield well, and we got into moles, but we forgot that you can use the molar gas constant at STP to change into DM cubed of any gas. I gave you that we were at STP. I also suggested that you use sections 2 and 6 of the data booklet. Section 6, of course, is just the periodic table, but section 2 had this value, this 22.7. So even if you didn't remember, if you just open up section 2 and you see 22.7 DM cubed per mole, all right, well, that's my conversion factor then if I need to end up in DM cubed. All right, BI was electron configuration of the copper atom. We had most recently reminded ourselves about transition metals in T7 day 4, but this was a little bit of a challenge because we had not seen electron configurations in a minute, but I was really happy many of us got that. For those of us who did not remember, well, copper, of course, is right here. That means that copper should be filled 4s and 3d, maybe up until 3d9, but copper is one of the 2 exceptions. Copper and chromium are the 2 exceptions in transition metals where we fill only 1 electron in 4s, and then that means that we need to fill 3d10 in order to get copper. So this would be 1, and then this is going to be a little hard to draw, but each of these was filled in to represent that 4s1, 3d10, which is the electron configuration for a copper atom. 2b and 2bii and 2biii, those are HL only. So again, we recently reminded ourselves about transition metals. Oxidation state, well, there we're looking at what charge it might have. It helps, of course, to remember that CO3 has a charge of 2 minus, and so then in order to make a neutral compound, we would have Cu2 plus. That's for BII. And then BIII, one characteristic of a transition metal. Hopefully you remembered something there. So for that, I might have accepted something like variable oxidation state or colored compounds or paramagnetic. What I did not accept was things that were general to any metal. So if you were trying to say something like malleable or shiny, well, that's all metals. So that did not earn credit, but anything specific to transition metals counted there. Most people got that point. All right, 2C, standard level and high level. So we went through all of those ways to measure a chemical reaction here in T6 homework 3. The most common things I saw there were kind of 2 things. One was some people just said something like syringe. It was really, really important that you mention the variable that we were measuring. So if you were using syringe or water displacement, that was to measure volume of gas. And we emphasized that when we made those graphs on the day that we did the experimental methods. I also had some people mention colorless or color change there, excuse me, and that was really astute to recognize that copper forms colored compounds. Copper 2 plus would have the configuration 3D9, meaning it would indeed be a transition metal, and so it could change colors. So color change, volume, color change, pH change, or change in H plus concentration, which you would have had from having an acid here to having water, which disassociates a lot less. All of those would have been acceptable. Volume of gas produced, I should say. All right. Question 2D and E. This was asking about drawing a graph and then calculating the initial rate of change. Well, the graph should have been decreasing and getting slower over time, just like we see here. Then in order to calculate the instantaneous rate of change, just like we saw in T6 homework 2, draw a tangent line at t equals 0 for initial rate of change, and then find the slope of the tangent line. Some people tried to talk about finding the slope of the reaction line. You do need to find the slope of the tangent line, otherwise you're not finding the initial rate of change. We should know that slope, of course, is delta y over delta x, or change in concentration over change in time. So this was D and E, should have been directly from this homework problem here. Finally, F, explain using collision theory, pellets versus powder. So a lot of people earned just 1 point here, and it was because of this word likelihood. So a pellet versus powder. Notice we had the same mass of both. It said that in the problem, that there was the same mass. And so if I have a pellet versus powder, well, the pellet has decreased surface area. And so when the reaction is first happening, when we're trying to react, only the particles on the outside, only the molecules on the outside will be able to react. So there's a lower likelihood of collisions, at least at the beginning. Whereas here, all of the molecules and all of the outside of the pieces of powder can react. Now, once the molecules on the outside of my pellet have reacted, the molecules on the inside will eventually be able to react. It's just not going to happen as fast because there is a lower likelihood at the beginning that any particular molecule would happen to have a reaction. So eventually, in both cases, all of the molecules should be able to react. It's just with a pellet, you have a lower likelihood, a lower frequency of collisions at the beginning until that pellet starts to break up and more of the reactants can react. So lots of people got 1 point for saying something about surface area. And then a lot of people miss that second point for missing that idea of like likelihood or frequency or something in that realm. All right, question 3. Question 3A was asking about graphs. That was taken directly from T6 homework 2. It was the opposite of the question I'd asked you in IB practice number 1. So the EA for the uncatalyzed reaction should have been higher kinetic energy, and this is in, of course, the Maxwell-Boltzmann. And then the EA for the uncatalyzed reaction, you should have drawn a peak, and the peak needed to, the reactants and the product should have been exactly the same. The only thing that differed was the peak and labeled with EA. For B, I'd given you this exact mark scheme, how the catalyst increases the rate of reaction. There really wasn't a way for me to ask that any differently. So it's the same exact question you saw in the homework. You, of course, had access to that mark scheme. So the 2 points you can see there. The alternative pathway with a lower activation energy, or you could have just said more particles with E above or equal to EA, which is another way to say that particles have sufficient activation energy. All right, question CSL. So higher temperature causes the rate of reaction to increase. We actually saw the same question in T6 homework 3. So there were kind of two things there. A lot of you got something about more collisions and said something about there being a higher frequency of collisions, so there's a greater chance that your reactant molecules will hit each other in the correct orientation to react. The other piece there was remembering why kinetic energy matters so much. And kinetic energy matters so much, we can see if we go back to A, it matters because of Maxwell-Boltzmann, because in order to react, we need the kinetic energy to be above the activation energy. So that was the other point, recognizing, all right, if more molecules have a higher energy, then more molecules are going to be above my activation energy. So with catalysts, the key is that you're lowering the activation energy. So even without changing temperature, that automatically makes more molecules above the activation energy. With higher temperature, well, if you picture the Maxwell-Boltzmann, with a higher temperature, you don't actually change. I'm going to put EA right here. You don't actually change where EA is, but you are able to put more molecules above EA. So that shorter, broader curve, this would be T2. And you can see there's more molecules above EA, so more molecules available to do the reaction. All right, C for HL was dealing with entropy and spontaneity. And then CI was dealing with enthalpy of solution. So enthalpy of solution, that was actually a self-study. It was linked for you in T15 homework 2. We had an example homework problem in T15 homework 2. We learned this formula here about enthalpy of solution, that the enthalpy of solution is equal to the lattice enthalpy plus the hydration enthalpy. So this one was pretty straightforward. You just needed to add the lattice enthalpy and the hydration enthalpy in order to get enthalpy of solution. The reason that works is that lattice enthalpy is going from solid to gas, and then hydration enthalpy is going from gas to aqueous. So in order to go from, from solid to aqueous, you just need to add those two. Excellent. And of course, you could also solve that like we did here in the homework as a Hess's law problem by writing out lattice, solution, hydration. Okay. And then the entropy and spontaneity, most of us did really well with that. The entropy, I was looking at the phase, just like I did in the homework with these two practice problems, where I was looking at phases. In this case, in this reaction, we were going from aqueous to gas, so entropy increases, more disorder. And then in terms of spontaneity, well, they actually gave us a delta H, I believe. Let's see. Delta H. I think at some point they talked about that, and then they gave it to us in this chart here. I know that in this reaction profile, this is an exothermic reaction. That means delta H is negative, and I just found out delta S was positive. I saw that in C. And so you could have used either of these to reason this out. I like picturing it like this. So I'm looking at delta H is, let's see, delta H is negative, that's this one, and delta S is positive, so spontaneous at any temperature. You could have also reasoned it out this way if I have um, exo, exothermic, positive increase in energy, that would be, again, always spontaneous. All right. Question 4, this was directly from the day that we talked about Haber process. This is one of those times where I told you this was going to be on the key assessment. It was indeed on the key assessment. So this is kind of that balance that we have to strike. We want low temperature in terms of Le Chatelier's principle, but not too low because industrially that would slow down the rate of the reaction too much. We want high pressure for Le Chatelier's principle, but we don't use a pressure that's too high because that's really expensive and hard to maintain. The IB actually said don't accept just high pressure is expensive, but I was actually pretty lenient on this question. So some people did say high pressure is expensive, and I gave you the mark, but notice how specific the IB really did want you to be here, mentioning like a compressor or the building, something about that being expensive. All right, final question. Question 5, standard level. This was answered really, really well. I was really happy with this one. This was really similar to another problem that we'd had where we looked at increasing volume. In this case, we're increasing the volume. So the points here, recognizing that increasing volume decreases pressure. Decreasing pressure favors side with more moles of gas. Specifically, in this case, we only have gas, but if you had a case where you had some gas and some not gas, that would be important. And then just counting. So there's 2 moles of gas here, 3 moles of gas here. So I'm going to favor the reactants. So that would be a shift left. All right. Question 5, HL. This was dealing with enthalpy and entropy in Gibbs free energy. So question A, we'd most recently seen something like this in T15. So this was using section 11, that's bond enthalpy. Remember, bond enthalpy is adding bonds broken minus bonds formed. The tricky part here, complete combustion of ethane gas, we're looking at standard enthalpy changes. Standard delta H for combustion. I know this is really tricky. One person did get this, or maybe more than one. Standard delta H of combustion is combusting 1 mole of non-O2 product. So if I have, let's see, this is ethane, so C2, H6 plus oxygen yields CO2 plus H2O. When we go to balance this, we need a 2, 4, 7, and 6. You could, of course, show the whole process here, but I'm just going to check. I think that's right. 14, 8, okay. But this is not a standard enthalpy change because there's 2 moles here. So I need to have 1 mole of ethane gas and then do half fractions to make this work. If you missed that, that was a really, really easy thing to miss. You could have still earned most of the credit here. It would have been -1 on A, and then as long as B and C were set up correctly according to that, I did ECF, which it means error carried forward, which means I did not keep penalizing you for B and C for that standard thing. So I know that was tricky. So this was one thing that was commonly missed. Some people did switch bonds formed minus bonds broken. Remember, bond enthalpy change is indeed bonds formed minus the bonds broken. And remembering to multiply by our coefficients. All right, B, delta S. Calculating delta S. Delta S is products minus reactants, the sum of the standard enthalpies of the products minus the standard enthalpies of the reactants. We saw that here in the slides. I also showed you that in a video. And then delta H, or delta G, excuse me, we saw again in this video or in the slides with the standard Gibbs enthalpy. Notice that you are using enthalpy and entropy. So this was one way that we found to find Gibbs free energy. But in this case, we were going to use delta H, the same thing that we saw here. Delta H equals delta H minus T delta S. This wouldn't make sense because we, of course, don't have because the question asks us to use the enthalpy and entropy, and in A and B we just found enthalpy and entropy, so we're going to use those answers to A and B to answer the question. And so we found this in A, we found this in B. So just plugging in your answers, the two things that I saw there, temperature needs to be in Kelvin. The other thing was the units need to match. So you could have either had kilojoules here and kilojoules here, or joules and joules. So one of these numbers had to be converted. And that was one thing that I saw in a couple people's. And of course, it would be kilojoules per Kelvin, or joules per Kelvin. So making sure that your units matched was the other thing that I saw there. All right, I hope that helps. As always, let me know what questions you have, and thanks for watching.